the cloud. Okay. So what are we going to do? We are going to finish the sampling of the Ising model, if you remember, to show that indeed it gives you an approximate sampling of the Ising model, and then we are going to do kind of what I believe is the most interesting thing in the Ising part, and even more exclusively from all the lesson, which is the graphical expansions of the Ising model. Okay. So why is it interesting? So just to recap a little, like what we have seen last time. So what do we know about the Ising model? Well, we know that it's a statistical model, so with fluctuation, it's a measure, okay, on some configuration. Those configurations, they can have like some kind of boundaries which are fixed. The energy of a configuration is what it's actually kind of, in some sense, related to the amount of disagreement between the spins. And it's and the probability like configuration will appear more frequently if the energy actually is low. And what we have learned last time is we have understood a little what it means to have a boundary. Okay, to have a boundary, it's kind of the same as to have no boundary at the condition on having the spin fixed. Okay, so at least we have understood this kind of thing. We have seen also so the dynamics we are going to do it. And so the next step will be this kind of diagrammatic expansions, which will be nice because they will really allow you to really understand more what's going on. So we will see that typically in a low temperature expansion, there are some curves which appears, and those curves are curves of disagreement. So you will understand the Ising model as more lines of disagreement. In high temperature, it will be actually lines of kind of alignment or actually influence. So we will see the Ising model as a model of actually lines, where the lines actually like from one point to the other point, it's like if there was an influence between one point to the other point in the Ising model. And then we will see also two other things. One which is related to FK percolation. So we will relate that to percolation with non-local term. And then at last to the most interesting part, I think, which is the current model, which is percolation, which we will be able already to write things in terms of probability inside a certain model of percolation, exactly the percolation we have seen before, with the only difference that now instead of having like a certain weight, like 1 or 0 on the edge, we will have actually an integer number on the edges. So not only it's open or not open, it's actually, we say how much it's open. So it will be nice because then we'll be able to relate, some kind of correlations which look kind of complicated in the Ising model. There's really a lot of interactions. It's really hard. As soon as there is interaction, actually, things are really complicated. In terms of something where things are totally decorrelated, and then we just look at a certain event. And this event will be kind of simple typically. If we look at the correlation of Ising model at 2 points, x1 and x2, we want to understand that. What we will do is we will look at this kind of new percolation system, and we will just look at the probability that the 2 points are related in this, are in the same cluster in this percolation. Okay, so it will be more clear and easy. There's what's going on. Okay, so let's do first quickly this sampling. So to remind you, there was two kind of sampling that we could do. Both of them are actually asymptotic. Okay, they are not exact. So which means that you need to wait a very long time, for a certain time at least, to have an approximation of the Ising model. Okay, so the first one is the metropolis Wilbur, and the second one was the EPFL. Each of them, if you remember, it was actually what we were implementing was random. It was a Markov chain. Okay, so we were looking at what is the configuration I am in, and then randomly I'm going to take a step in the space of configuration, depending on where I am, not depending on the previous past. Okay, and I was thinking you had a configuration sigma. From sigma, you could look at sigma x, where you are going to exchange. You're going to change actually the spin. So the spin at x is changed, and we take x uniformly. And then we were looking at actually the exponential minus beta h of sigma x, exponential minus beta h of sigma, those two numbers, and depending on those two numbers, we're going to either keep the same configuration, or we are going to change. So that you remember, in the metropolis glober, it's a kind of like we try to minimize, in some sense, the energy. So if the energy is actually h of sigma x is lower, then we are going to change. Okay, so h of sigma x sigma. So we keep sigma x. This is bigger than of h sigma. So if the energy actually increases, what we are going to do is we are going to flip, but with a certain energy, with a certain productivity. So let's probe this. So if the energy is very, very, very large, this is actually almost equal to 0. So you are not going to keep sigma x. Okay. So you agree to have like some kind of fluctuation, takes configuration which are with a slightly bigger energy, but not. I mean, you won't penalize if the energy is very too high. Okay. And in the heat bath, it was simpler. You look simply at this property here. So with property that we keep. And so the very important word is, well, this defines those two dynamics. They define Markov shape. We are going to look at the matrix E sigma. It's a priority that by n plus 1, I'm going to be equal to eta, knowing that. So the main important object in those dynamics is given by this transition matrix. If you know this transition matrix, then you know actually both of the dynamics. Okay. So the main theorem is the following. Is actually just application of Markov chain theory. So when n goes to infinity, the distribution of xn converges to is the thing which tells you that, okay, the algorithm actually works, at least asymptotically, it works. Okay. So another way to say that, so little remark. If, at the beginning, I need to initialize my algorithm. So I'm going to sample x0 according to a certain measurement. So we sample x0 according to a certain measure mu. Okay, so which means that the probability of x0 is equal to sigma is equal to mu sigma. Okay. Now, what is the law? What is the probability that x1 is equal to sigma? Sigma. Well, it's equal to, I need to look at where I was at x0 and what is the probability that I transition from the sigma 0 to sigma 1. So it's going to be the probability that x0 is equal to sigma 0 times the probability that I go from x0 to x1, which is given by this matrix, transition matrix. So it's p sigma 0, sigma 1. And I'm going to sum over all the sigma 0. Now, if I see, so this is mu sigma 0. If I see mu as a vector, okay, which is indexed by all the configurations I can have, well, this is simply mu times p, and I look at the coordinates sigma 1. Okay, and so more generally, I recommend you that after if you know, tell me. But, so more generally, what you get is the following. Okay, the measure is given by simply taking the first distribution. So first, yeah, I didn't. New transpose. Okay. I take the distribution as a line vector, and I multiply by p to the power n, and I get a new line vector. And this new line vector is my my measure at times. So the theorem here at the end, you know, I can write it as purely algebraic theorem. It tells me that whatever the mu I'm considering, and whatever the p is, like either the metropolis global or the EPFL, this will convert to mu. So we simply have to show a kind of theorem which is purely algebraic theorem. So this is a classical theorem in Markov chain. I'm going just to give you like the insight of it, not necessarily prove everything, but before giving you the theorem, I need to give you the main characteristics of my Markov chain. If you have a Markov chain, let's say, you know, imagine your Markov chain is actually just a kind of simple random walk on the graph. And this graph, it's actually disconnected. Okay, so imagine you have really a random walk, but on a graph which is disconnected. Can you expect actually, you know, to have convergence of the measure under this Markov chain to something which is unique? Is there a dependence in my algorithm? Like, is there something like, okay, I might not get something unique?
Depends on the relative mass. From the relative product mass.
So, yeah, I mean, or to say it, I can begin here. And then in that case, my random walk will stay here. It might converge to something, but at least the measure, you know, it will have zero mass here and all the mass here. Or I might begin here, and then I will get the opposite. So you see that it's not all Markov chain, it's not for all Markov chain that you will get a certain property like that, where whatever I do at the beginning, if I do my Markov chain, it will convert to something which is unique. No, I mean, in this case, it's not the case. Typically, what I will need is, I will need to have a kind of irreducibility, which means that I can go from any point to any other point. I need to have, you know, that the Markov chain can really spread out and visit everywhere. Okay, this is the first thing I need to do. There's also something which is important, which is, imagine I have just this simple random walk on this graph. Can it converge to something? Well, the thing is that if I begin, you know, everywhere here, then I will be here, and then next time I'm here, next time I'm here, next time I'm here. And so you see that, you know, I will have a kind of periodicity actually in what I'm seeing, and I don't get a convergence like really for any n I convert to something. And this is because actually, you know, there is kind of periodicity in a different path. So typically, I mean, when I look here and I look at what is the length of the path in order to come back to itself, I see that actually it's only multiple of 2. And the same for this guy also. So I see that actually all the points, when I want to come back to themselves, I will have to take path of length 2 times n. This property is something that we don't like, and so what we want is something called aperiodicity, which tells you that this will not happen. Okay, which tells you that actually when I'm at a point, well, okay, maybe at the beginning we'll have to do a path of length 2, maybe 4, maybe 6, but after a certain time, I'm sure that I come back to itself with any length of path I want. So I want that when I'm at a point, there's at least a certain moment where I can find a path, you know, of length equal to this and all the ones after. Okay. So altogether, what we want is the property that is important is we say that Xn is aperiodic and irreducible if there exists a certain moment such that for any other moment bigger than this, or any points in my graph, okay, then I can go from x and y with a certain strictly positive, strict positive measure. Okay. So you see that there is inside there irreducibility because I can go from x to y, and at the same time I'm asking that actually for any of the points, any of the couple at one moment, actually, I will be able to go actually from x to y with a certain length. I mean, if I give me a time m, I will be able to go from x to y, whatever the m is bigger than m. And so the main theorem is the following. Now, if you have these 2 conditions, then it's enough to get this kind of results. So what is the theorem?
You can take extra graph with state sigma, with point sigma, and with energy function 8, and then it will work. So it doesn't have to be. So sigma.
Yeah, typically the metropolis glober, metropolises are actually something very general that you can do for anything where you have configuration space and energy. If you want to sample the Boltzmann exponential minus this, you do the metropolis and it will work. I mean, you have to find it. I mean, you have to. The only thing you have to do is to know, what is the step. Like here, the step is kind of natural. Is I choose a point and I switch. So, but as long as you manage to find a natural step for your problem, then you can do the metropolis and it will converge to your Boltzmann.
We don't have to be on the hyperloop.
No. I mean, if you have a conversion space of things, I mean, whatever, and you have an energy in it, and at the same time, you know that, at the same time, you have this kind of notion of neighbors that you can define. Then this will give you. Okay, so the theorem that is important is the following. So if the transition matrix is I will say that the random walk is aperiodic, but also that the transition matrix is kind of equivalent. Okay, to give me the transition matrix or the macropole. So if this is aperiodic and irreducible, then for any measure mu, of course, probability measure on the underlying space, this will converge to mu where so it's the unique stationary measure. What does it mean stationary? Well, it means that if I begin with this measure and I do a step, then I get again this.
If the convergence is uniform, like at all points.
Well, here we have I mean, I'm sitting where I'm in the finite thing. So, okay, so why is this natural? I'm not going to give you like all the proof. I mean, and it's not necessary to know the proof for you for the exams, but at least I give you like a hint of the different steps which allows you to get this result. So why is it true? Well, in fact, what we are really looking at, it's just, I could have looked at this instead. Like I can take the transpose, because here I'm multiplying with a line vector. We are more used to multiply by column vectors. So in fact, what this tells you, it tells you that, well, if I look at the transpose of my matrix P, then I can put any measure here. I will get conversions to the unique new stat transpose. Now this is 1. This tells you what? It tells you that actually it's the unique eigenvector of P transpose. Okay, so what it's telling you, this theorem, is tells you that, well, if you have P which is apertic and irreducible, then when I take P to the power T to the power M, like P transpose, I mean, to the power M, you make this a column vector which is normalized, so that it's a probability measure. It will convert to another probability measure, which will be actually the unique eigenvector of P transpose with eigenvalue 1. Why is it not like totally surprising? Well, if I look at P, well, what do I know about P? Well, if I do P times 1, 1, 1, 1, 1, 1, 1, so this gives me 1. Well, I'm just looking at P, X, Y, and I sum over all the Y's. But this is the probability that I'm at Y, knowing that I was at X. So this must sum up to 1. So you see that because P is a transition matrix, 1, 1, 1, 1 must be an eigenvector of P with eigenvalue 1. Okay, so this tells you P has eigenvector value 1. P, can it has like an eigenvalue which is bigger than 1? Well, if it has an eigenvalue which models it's bigger than 1, when I do P to the power n, I will be able to find an eigenvector so that P to the power n times this vector will actually explode. And it's not the case because we are looking at matrix. We are looking at random Markov chains, and so when I do P to the power n, it's just another transition matrix. Nothing can explode. So because of that, you have that the eigenvalues P must be a modulus less than 1. Now the thing is that, well, if P has this kind of eigenvalues, then P transpose will have the same kind of properties. So for P transpose, the eigenvalues have modulus less than 1, and there's 1 and 1 as eigenvalue.
It should be less than equal.
So yeah, for all the others. Okay, so when I do P transpose to the power n, what will happen? Well, actually, all the eigenvalues which are less than 1, strictly, all the, when you're going to decompose a thing in the different space, like a Jordan block or things like that, those guys will actually disappear. Okay, everything which is related to an eigenvalue, which is of modulus strictly less than 1, will actually disappear. So the only thing which will remain will be actually the decomposition of your initial vector inside kind of the space of eigenvectors or Jordan block of the eigenvalues of modulus equal to 1. Now, the good thing is we have the following theorem, which is actually the key really of all this.
This is correct, is that there actually will be the eigenvalues 0 and 1. Everything which was less than 1 becomes 0.
Mm-hmm.
The 1 which is 1.
Yeah. Yeah, but the thing is that you could have like another one of it. First, you could have like the eigenvalue 1 could be associated with a vector, like a space of dimension 2 or more. Okay, and so in that case, well, like typically, if everything was diagonalizable, if you have like 2 eigenvectors of dimension 1, you know, then if I take those 2 vectors and I normalize them to get the measure, if the coefficients are positive, then I will see that depending on the guy I put here, I will get 2 different limits. So I must be sure that this doesn't happen, and also I must be sure that there is no other eigenvalue of modulus 1. Okay. Now the good thing is that you have the theorem of Frobenius. So if you have matrix A, such that AX, Y is strictly positive for any X and Y, then there exists a certain lambda strictly positive, such that all the eigenvalues are of modulus strictly less than lambda, except for the eigenvalue lambda. So lambda will be an eigenvalue of A, and lambda will be simple. It's a simple eigenvalue. So which means that like if A was like, if you write this in like triangular form, you will have only one time the lambda. Okay. And so it's exactly what we were like what we needed, except that we are not sure that P is strictly positive. The P doesn't have this property. But P, what it has is it's I know. So
every entry is positive, or you have a positive.
All the entries are positive.
On the entries, and basically means that there are, if the matrix, there is a maximum eigenvalue, and maximum eigenvalue example.
So what you will have is that you will have here. On that here, this is an eigenvalue, and then the others are very strictly inside that. And this is simple. And actually, the eigenvector associated to it, you can take it with something I didn't say.
The result is that the largest eigenvalue is simple.
It's simple, and all the others are That's this one is real. But this one is real. That is simple. And that the eigenvector associated to it can be taken like this positive.
It doesn't have to be symmetric.
No.
Simple is you mean the eigen spaces of the
yeah, exactly. So you don't have this problem of how do I decompose my initial measure in the space associated with the eigenvalue lambda, because it's only dimension 1. If you had like dimension 2, then I can take this eigenvector of this eigenvector, and then I might have like two different conversions. Okay, so
So
for A,
when A is not symmetric, the other eigenvalues they can be complex. Like,
yeah.
and okay, so
Yeah. But there will be a.
so they're not okay.
Yeah. Okay. So you need to have all the entries strictly positive. P is not strictly positive, but we know that there is actually, a moment where P to the power n is strictly positive, and we know that P transpose to the power n at one month it has strictly positive entries. I will write it just like that. So which means that this guy here it will have one will be an eigenvalue of that. It will be simple. Okay. And because of that, you see that PT itself cannot have one with more multiplicity. Okay, it will contradict that. So it tells you that at the end, PT has one as eigenvalue. And actually, you can also show that in fact, you can take V such that the coordinates are positive. So if I normalize V so that I have a measure, what it tells you is that there's a unique measure which is invariant by P. And it tells you that actually all the other parts, when you decompose your initial measure, when you decompose it into the eigenvectors, well, all the others will disappear. The only thing which will remain will be actually a multiple of this eigenvector. And since you have a gravity distribution, it has to be this stationary measure. Okay.
Just make sure. So we have all ones as an eigenvector, but V is an eigenvector of P transpose with the same eigenvalue. You have all ones as an eigenvector
Of P.
Antip and P.
Yeah, V is okay. Okay, so this is to give you like a feeling of why things are true. And again, you see that it's only about algebra. You kind of forget about T. Now, the thing that how do I find this P transpose V? Like how do I find this V or this new stuff? This is something which looks complicated. Okay. So the theorem, what we have seen here is the theorem tells you that, well, if you manage to show that the Markov chain is aperiodic and irreducible, then you will have conversions to the staff measure. Okay. How do I show that first of all, the Ising model, Ising measure will be the invariant measure? The thing that if I really write, P mu is equal to P, if I try to write that, you are summing over all the configurations of Ising model, it will be a very big, huge sum. It will be complicated. If I want to know, I want to show that. Sorry. I want to show that the Ising measure is a stationary measure for my Markov transition. Okay. Normally, I have to show that. This is complicated, at least because this is like 2 to the power n times 2 to the power n matrix. Okay, so you don't want to do this kind of computation. Yeah.
Of the theorem, is it true that the rest of the eigenvectors for other lambdas are actually complex?
I don't care. I just care about it to be a strictly split.
Yeah, because they converge to something that is zero.
Yeah.
But we can have if the eigenvector would be real, then it could mean that
it will converge to zero still. We'll have a lambda to the power n, which will destroy all the rest. Because the modulus of lambda is strictly less than 1.
Or else we could say that maybe because the complex eigenvalues are bounded, so the singular values would also be bounded.
No, I mean, I'm just saying, you write your matrix in the Jordan form, what you will have is that in block. So one block will be actually 1. This one will get. The other one is lambda diagonal plus nilpotent. And if I do lambda diagonal plus nilpotent to the power n with n large, well, actually, because the diagonal, you write what it gives, it converts to 0, this part. Okay. The thing about it as Jordan blocks like diagonal nilpotent thing, and all those blocks will just disappear. Okay. Okay. So what I want to give you is to like, can I have like something which is kind of easier, a condition which is easier on a measure, such that, you know, if you give me this measure and the Markov chain, I'm like, okay, this one will be the stationary measure without doing all this big computation. Okay, so let's look what it gives. So this tells you, okay, if I do the sum over all the x, oh, sometimes I put x, sometimes I put sigma, and I hope you understand that. Okay? Okay. So here I'm looking at the general framework. What I want is this. And as I told you, this is complicated because I'm going to sum over all the elements on your graph of the Markov chain. So in the Ising model, it's like 2 to the 4. So we don't like that. Yeah, but there is like P, what does it satisfy? P satisfies the following thing. If I do sum, this is equal to what? This is equal to 1. Let's insert that here. Okay. Now, there is one case where everything is trivial. If this is equal to that, then the two sums are equal. So we say that mu satisfy the balanced equation for P if for any x and y, I look at the weight that I'm at x times the probability that I go from x to y is the same that actually if I begin at y and I go from y to x. So I have a kind of balanced flow. It's a measure so that I have a balanced flow between x and y. What I've written here gives me the following lemma, which is actually super important. If mu satisfies balance equation, for P, then mu is a stationary measure for P. No, it's not. Because what I'm saying is that this is equal to that, then the sums are equal. But I could have some cases where the sum is equal, but I don't get the balance equation. As a matter of fact, each time we are working with random walks, when Markov chain, and you want to measure, you want to know the measure, I mean, quite often it's balanced actually. But it's not necessarily. It's not an if and only. It's a way to find it, and it's a way to check, but sometimes might be not the case.
So we just use uniqueness, you know.
So yeah, so here it's true for any P. Then if P is actually now aperiodic and irreducible, then mu will be the unique stationary measure. Okay. So now let me wrap up everything. What we have seen is the following. If you have a Markov chain, if it is aperiodic and irreducible, then I know, because of this kind of whole thing we have seen, the Period-Frobenius thing and everything like that, I know that if I begin the Markov chain with a certain measure and I let the Markov chain live for a certain time, it will converge to the unique stationary measure. First thing. So when I have Markov chain, what I check is it's aperiodic and irreducible. Then second thing, if I want to know what is the stationary measure, or if I want to check that this stationary measure is a certain measure, let's say the Ising measure, what I will check is simply the fact that I have the balance equation, which will be something very simple because P is very simple in all the cases we have seen. Mu x and mu y, they look complicated, but if you think about it, in fact, mu x is just proportional to the energy of the configuration x, the same for y. And how do they differ? Well, they only differ because I switch a spin. I flipped a spin. So in fact, mu x over mu y, it's something very simple. Okay, so it will give us very simple equations. So let me give you like a hint. Again, I don't want to spend too much time on that. I think the diagrammatic expansion is way more important. But so we need to check that. Let's come back to the Ising. So we need to check that for the Glober and for the heat dynamics, bath dynamics. You want to check that it's aperiodic plus irreducible. So let me give you like the hint for, let's say, the heat bath. For the Glober, there is one little step to be careful about, but it's not complicated to go around this little. If I look at the heat bath dynamic, can I go from any configuration sigma to any configuration mu? Well, at each step, I mean, I can just randomly select actually the first spin. There is a property that I flip it, and then I take the second spin, because randomly it happens that I chance. I take the second spin, I flip it or not, depending on if the two have the same spin at this point. Then I take the third vertex. There is a so you see I can go from sigma to eta. What's eta? Okay. By eta using actually my Markov chain. There is a certain property that I can go from sigma to eta with a maximum of path of length of size actually n, where n is the number of vertices. Okay, if there are n vertices, I know that I can go from a configuration sigma to eta by doing at most n steps. Okay, and there is a certain property of this happening. No, but it exists. Okay. So this is nice. The first thing is nice. So it tells us that it's irreducible. Now, why is it aperiodic? Well, the thing is that if I have a path, which goes from sigma to eta, if I go from sigma to eta, I'm under the heat bath. So under the heat bath, what's happening? I take randomly a guy, I flip or not, but there is a property that I don't flip at all. So there is actually a strict positivity probability that I stay exactly at the same configuration. So if I know that I can go from sigma to eta with a path of length, let's say n, I can do for n plus 1 because I just say, well, but I can stay, and then I go there. And then I can stay, I go there, and I get n plus 1, n plus 2, n plus whatever you want. Okay, so this shows you that it's actually aperiodic plus irreducible. Exactly the same argument can hold also for the Glober dynamic, almost, except that there is one case, is if you have a configuration where you have everything disagree with each other. In Glober, why would you stay at a certain configuration? Well, you would stay at the configuration if you manage to, to pick a guy such that when you're going to flip it, the energy is going to increase. So if you have a configuration such that I know that I can take a vertex, I can flip it, and I'm sure that the energy will just increase, then there's a probability that you stay exactly where you are. Okay, this is a global dynamic. There's only one case where you cannot do that. Well, it's actually where you are +1, -1, +1, -. Okay, but it's not a problem because you do everything without considering this +1, -1, +1, -1. You know that you are going to be able to go from any x to any y with path of size n and +1 and whatever. And then you say, well, if I am at +1, -1, what do I do? Well, I escape this guy. I know that I can escape actually this guy to arrive to another configuration with a path like n and +1 and +2 and stuff like that, and then I come back. Okay, so you can always, put in the middle. No, the only problem is to know what's happening if you are at the one with disagreement everywhere, and can I come back to itself with path of size n and +1 and +2 and +3. Okay, this might look complicated, but actually what you can do is you can intercalate, like you can put in the middle another guy, which is kind of easier to understand. Okay, so this is why this is aperiodic and irreducible. So you know that it will converge to the Ising measure. Okay, and well, as an exercise, so you will do on the exercise sheet, you will see actually that for the Glober, I think, no, it's for the EPFL. For the EPFL dynamic, you will see that the Ising model satisfies the balance equations in the exercise. Okay. As another exercise, you can do it also for Glober. I'm not going to do it, okay, but you can do it also for the Glober. Okay. And I mean, well, yeah. Okay. Okay. So to wrap up what we have seen that all those algorithms were just implementing Markov chains. We were able to show that those Markov chains were actually aperiodically reducible. We can apply the theory which tells you, okay, then when I take whatever measure at the beginning, it will converge to the unique stationary measure, and then you can check that the Ising model is actually the stationary measure under those dynamics. Okay. Well, just okay, to give you a hint again, if you have the Glober inequality, if you have the Glober dynamics, let's say that x has an energy less than y, then you know that if x has a no, let's say that no, y has energy less than x. So you know that this property here. So y has an energy less than x. So for sure, if you have picked exactly the good. Okay, so let's say, okay, I do it again. Oh, sorry. Let's do it now that I begin. Okay, so Glober. So that's you don't trust me, here we go. I want to show that and let's assume that this guy has an energy less than this guy. So what was the property that I go from sigma to x to sigma x? It's not exactly one because you have to pick x first. But once you have picked x, when you know that when I've chosen my vertex randomly, I choose exactly this x. When I know that, then conditioning on that, it's 1. Okay, so this property is just 1 over v, the number of vertices. Okay. This one is proportional to exponential minus your sigma, This one is proportional to that, with the same proportional constant. Is this true? This tells you actually that the probability that I go from something to something which has higher energy should be of the form 1 over v, which is, I think, I have chosen exactly my x, times the ratio of the two energies, which is exactly what we have defined. So in some sense, I mean, you see here that then it must be really more general, I mean, this setup, okay? And in some sense, you could have found this algorithm just by saying, okay, I want something so that the measure is a stationary measure, plus I want to minimize the energy for sure. If the energy is lower, I really want to go down, but I can allow some little, freedom to go to energies with bigger energy, configuration with bigger energy. Okay, do you understand this? Okay, so the balance equation is actually very trivial. It's actually a way to get the thing. You will see the balance equation for the EPFL is slightly more complicated, but it's not too much more complicated either. Okay. So I hope you trust me now that when I tell you, okay, the global and the EPFL dynamics will convert to the Ising model. It's purely those two mechanisms. Okay.
So that could be the following. So we take the transition probability phi as sigma x from sigma. Then we can derive a ratio of mu sigma divided by mu sigma x.
Okay, so what we are going to do now is what I very like grammatic extensions of the Ising model. I decided to kind of give you like 4 of them and to kind of try to give a unification of the 4. It's not always the case that they are given like that, but I think, I mean, at least for me, it was I felt stupid not to understand that the 4 were actually the same thing each time. Okay, so what we are going to do first is to expand the partition function with a certain boundary, so which is defined as the sum over all the configuration with the boundary exponential beta h of sigma. So this is the first thing we are going to do when we are going to want to do a graphical expansion of the Ising model. And then the second thing we want to do is not really the partition function that you are interested in. What you are interested in is to expand the correlation functions. But how do you write the correlations? So what kind of correlations? Well, the only correlations we are going to be interested in is the product of the spins at certain points. Why is it the case? Well, it's because in fact, if you have that, any function on -1, 1 to the power a number of vertices actually can be decomposed into a linear span of this sigma. Okay, it's not something too complicated to show. Well, okay, I give you again a hint. Why is it the case? How many sigma A do you have? Well, you have as many sigma A that you have the choice of A. How many choices of A do you have? Well, you have 2 to the power n. What is the dimension of the functions on -1, 1 to the power n? Well, it's 2 to the power n. So at least you see that the number of functions that I can create here is exactly the same as the dimension of the functions on -1, 1 to the power n. Okay. And what's more, we will see that, but those functions, those sigma A, actually they are orthogonal. So when we are going to sum over a sigma product of the sigma x, actually it will be equal to 0, except if A is equal to the empty set. And this gives you kind of an orthogonality of the functional sigma A. Okay. Yeah, exactly. Okay. But at least, I think I can, you can trust me now that at least I have 2 to the power n kind of different functions I can create on the configuration space. And the space of function on -1, 1 to the power n is exactly 2 to the power n also. Okay, so we want to expand that, and this is what? This is given by some product of sigma x belonging to A, exponential beta minus sigma over the partition function. Okay, so what we will do is the expansion that we had here, we can put it here, and we can hope that the same ideas we had here, we can also use them in order to express the upper part in terms of diagrams. This guy here, I'm going to call it ZBA. Okay, so here's the partition function with no spin inserted. This is the partition function with spins inserted. Okay, so those are the 2 things we want to do. And now the question is, what does it mean to expand sigma? So I gave you like the idea. So how do we do one? The thing we are going to do is we are going to write Z. So it will be like a lot of computations like this part, but don't be afraid. At the end, it's very super simple. Okay, so it might be like more cumbersome now, but we'll see at the end when it's the simplest part of all the thing, and it's the one which gives you the most insight. So I want to write exponential minus beta h of sigma. But what is it? It's just exponential beta sum over all the edges, sigma x sigma y. That I can write also as sum over sigma, and then product over all the edges, sigma x sigma y. Okay. So I take this. Now,
The very beginning, where is boundary.
B is the boundary, yeah. It was notation last time. Okay. Now the thing is that if I look at the function -1, 1 to r, this lives in a space of function, okay, which is the dimension 2. So what I'm going to do is I'm going to take either a basis or a generative family of functions, f1, f2, and maybe more, which will be either basis or generative function family of the space of function which goes from -1, 1 to r. Okay, so which is a dimension 2. Okay. And so what I can do is I can expand this function in terms of my basis or my generative. Okay, so I can write this as, well, it's a sum, product, and here I'm going to have the sum over certain index. So if it is a basis, the index will be just 1, 2, function f1, f2, which will give me my basis. But if I don't take a basis but a generative family, I might have more functions. So I can decompose the function I have here, so this function here, in terms of my basis f1, f2, or f1, f2, and so we will see very quickly what is the kind of function. I can even tell you, okay, what kind of function can I take? Well, I could take, for example, all the polynomials. So, which means f1 will be that, f2 will be that, f3 will be F2, no, F2, F0 will be that, F1 will be that, F2 will be that, and you keep on. Exponential beta sigma, I can always expand it into a Taylor expansion. Okay? So I will have an expansion of this one. What can I do? Yeah. Because I mean, I can't take a generative family. So we'll see. Okay.
It's not minimal.
No. It's a generative family. It's not a basis. Okay, but we will see why. I mean, like during a long time, to be honest, I was thinking, yeah, why don't you do that? And then I was thinking, oh, but it's totally dumb because, well, this is just a function of one. So it's totally dumb. And nothing can be done with that. As a matter of fact, actually, the easiest way to prove a lot of things is to do this. And that's crazy, actually. It's the current expansion. And yeah, we are going to see why.
So our efficient AI are unique.
No, they won't be unique here, but there is kind of a unique way here to expand naturally on this functions here. Okay, which is just to use the Taylor extension. Okay. So this will be actually equal to the sum over sigma. And here what do you have? You have a product of sums, so I can expand. How do I expand such thing? What I have to do is I have to choose for any edge. I have to choose one guy here, one guy in my sum for any edge, and then I need to multiply those things, and I need to sum over all the ways to choose inside my parentheses. Okay, so to be more clear for people, imagine you have something like that. How do I expand that? Well, what I'm saying is that I'm summing over all the way to choose either this guy or this guy. So for each parenthesis, I have a choice. I'm going to sum over all the different choices I have. Like, first of all, I take this guy here, take this guy, take this guy. So I sum over all the choices like that I have. So for any parenthesis, I choose one guy, and then I multiply everything I have chosen. Okay? This is how you expand a product. Okay. So, which tells me that here, what I have is I have to sum now over all the IE, E belonging to the edges. So for each edges, I will have an index. And then I have to do the product over all the edges. FIE, sigma X, sigma Y. Okay? Now, this sum here, I can put it in front. Yeah, I can put it actually here, okay, because there is no sigma here. I mean, and actually, this product of AIE doesn't depend on my configuration sigma. So I can also, put in fact the sum. I can bring it back in front here. Okay, so what do I get is I get it's the sum over all the weight you put index on the edges. I will have a product over all the edges of a certain weight. And then I have to do the sum over sigma, product over all the edges, FIE sigma X, sigma Y. So now you see, instead of having a sum of their configurations, okay, -1, 1 over all the vertices, what I have is a sum of their configuration where now I have an index on the edges. I have a certain weight, which will depend on the configuration I have on the edges, times something here. But something here, I mean, it's just functional. G of IE. Okay. The certain functional of the choice I've made on my vertices. So if I want to simplify this expression here, what we have to do is, can we actually compute this in some cases? Can we do something with that? Can we would be nice if there is some cases where this actually will simplify. And this is exactly what we are going to do. Now, what's happening if instead of having Z, I was looking at ZA. If I'm looking at ZA, I will have sigma A here. I will have sigma A here. I will have, I don't care about, I will have a sigma A here. The sigma A will still be here. And so at the end here, I have a sigma A. And so I have a GA. But you see that introducing the spins inside my correlation function, you can do exactly the same thing. I just don't touch my sigma A. I just let it here. I do the expansion, so which means all this I expand it, all the exponential I expand it. I expand the product, and I have the sum. The sum I bring inside, and then now I have something else to compute, but which looks kind of the same thing. Just I have the insertion of spins. Okay, so it looks a little abstract. I know, but is to tell you, like, the fourth thing we are going to do is just this. Okay, so
From the definition of ZD, the sum over all configurations of the boundary, but the energy is computed as a whole.
No, here it's not on the boundary. It was there was a notation last time I said it. I'm looking at. Oh, sorry, maybe
Boundary is fixed.
So it's the function on the vertices which satisfy the boundary. Okay. So let's give me an example. Maybe let's. Okay, I wanted to make it even more abstract, but maybe not. Let's not. Let's take a ready example. High temperature. Expansion. Let's begin with that, or let's begin with. Well, let's begin with the low temperature expansion still, or no, like the high temperature expansion. So to do the high temperature expansion, we have exponential beta. Sigma, we would like to express that as a sum of functions which are easy. So as I said, one of the ways to do is to say, well, go to that. Okay. If we stick on that, then it will give us the current representation. But we are not going to do it now. Instead of that, what I use the fact that sigma, it's either -1 or 1. So sigma square is just equal to 1. There's a function equal to 1 all the time. Sigma to the power 4, it's always equal to 1, like that. So what I get is that in fact I can write that as 0 belonging to 2, or going to 0 to infinity of beta to the power 2n over 2n factorial. So I'm considering just the even part, plus the sum beta 2n plus 1 over 2n plus 1 factorial times sigma. Okay. Now, if I look at what is that, this is just so it's like the exponential, but I just kept the pair the even part. Okay. So how do I keep the even part of the exponential? Well, I look at this gives me the even part of the exponential. But this is what? This is cos h beta. So this is cos h beta. Plus, and I take the odd part of exponential, so it's sin h beta sigma. Okay, that I'm going to write it in fact as cos h beta times 1 plus tan h beta sigma. Okay. So I have an expansion where, well, I have a constant here, so this constant, what's going to happen with this constant It's just that in front you have a constant here for any edges. So you can put it actually totally in front. Okay, it will give you just cosinus h beta to the power of the number of edges you get. Okay, and then the function that you're considering is just the constant function, and the function which to 1 gives you 1, minus 1 gives you minus. Okay, so let's apply the thing here. What do we get at the end? Okay, for once I do it I do it again. You have the exponential beta. You would it like that. You expand. So instead of this expansion here, what you get is 1 plus term h beta sigma x sigma y. So again, you have this. Now you expand. But now, how many things you have? Either you take the one, either you take the other one. So the indices actually it's kind of 0 or 1. It's like, do I take the edge? Do I not take, or do I not take the edge? And do I take the edge? Okay. So maybe I can write it. Okay. I begin here, and what do you have is sigma product over all the edges, and then you have the expansion. So you will have in front the cos h beta to the power of the number of edges. And here you have 1 plus term h beta sigma x sigma y. You expand all that. So I need to know when did I choose sigma x sigma y. So I will have cos h beta to the power of the number of edges times the sum over all the sigma. Again, and here I have to sum over all the subset of edges. So I have to choose a subset of edges. And I will have some h beta to the power the number of edges in my subset I've chosen, because E is the subset for which I'm taking this guy here, times the product sigma x sigma y, where x, y belong to the subset. Okay, so it's exactly what I'm doing here. Okay, so this is now equal to plus h beta E, and the sum I can bring it here. I sum over all the edges, all the subset of edges. I have a weight. And now I'm summing over all the sigma and the product sigma x, sigma y, x related to y, and the edge belongs to E. So you see that I'm exactly in this situation here. What I need to compute is this guy. What is it equal to? So I'm going to erase both because I want to keep that to keep. At the end, I have that, and I need to compute this guy here. Okay. So what is it equal to? Yep. Let's put it like that. So the first lemma, which is very simple, is the following: is that if I do the product of all the sigma x, sigma y, x related to y, and xy belongs to the set of edges. This is equal actually to sigma, the sources of E. So where the sources of E is equal to the vertices, such that if I look at the sum over all the edges where x belongs to the edge, the number of edges in E such that x belongs to E, this is 1. So remember, this is a subset of the edges of my graph. Okay, so first of all, I have something of this one. I take this edge, I take this edge. First of all. Okay. This point, it belongs to two edges, so it's not in the source. This guy, it belongs to only one edge. Okay, so the number of edges it belongs to, it's even, it's odd. And so it's the guy in the source. Okay, this is the definition of the source.
Sigma index with set is the product.
This is like, as always, it's the product over. So indeed, so why the lemma is trivial? I mean, because what I'm saying is actually just this. And this is normal because if you look at the x, which is not in the source, it means that it belongs to an even number of edges. Which means that here, it appears an even number of times, but sigma x to the power 2n is equal to 1. So if a vertex appears an even number of times inside this product, I don't care about it. You see? So typically here, if I have x, y, z, and I look at this product here, it's sigma x, sigma y, sigma y, sigma z, sigma z. Sigma y, sigma z. You see that y appears 2 times, so I don't care about it. What I get is sigma x, sigma z. Okay? So this is the first lemma, which is very trivial. Second lemma. Yeah, that the sum of all the sigma belonging to -1, 1 b sigma a. So I'm going to do the case where I'm a free boundary, or 3n plus. Well, 3n. This is equal to 1. So there are two cases, depending on the fact that the boundary is free or the boundary is plus. I assume that I'm in free boundary. If I am in the free boundary, then it's equal to 0 if A is not equal to the empty set. And it's equal to 2 to the power v if A is equal to the empty set. In the case where you have plus boundary, what you get is 1. If A belongs, so instead of being free or not free, now you have a boundary. If A is actually inside the boundary, okay, you see that sigma A will always be equal to 1 because we are in plus boundary condition. Okay, so in fact, the condition will be the following. If A belongs to the boundary, and if A does not belong, is not included in the boundary, then it's equal to 0, and here it's equal to 2. Why is it so? I'm going just to explain you this. If A is empty, sigma A by convention is actually equal to 1. We are just summing over all the sigma minus 1, 1 to the power number of vertices, 1. So this is equal to 2 to the power v. Now, if A is not empty, what I can do is I can pick a guy here, and I split all my configurations into 2. The ones where the spin is equal to 1, the one where the spin is equal to -1. As a matter of fact, when I'm going to change the spin to 1 to -1, well, my sigma A is going actually to take a minus. Okay, so and how many? So which means that I can pair actually my configurations, taking instead of saying I sum over all the sigma such that I'm going to pair them, where each time I pair, I take a configuration everywhere, and then I take the configuration with a 1 here and a -1 here. Those two actually will cancel, and I have paired everything together. So I will get a 0. Okay. And so this is nice because it tells us that, well, this guy here, now, if I put everything together, this guy is just 2 to the power v, and the indicator function that the fact that the source of E is equal to empty. So we obtain the akntQ expansion I will write it after a little better, but it tells you that, well, the partition function, I can write it as some things which just depend on the number of edges, the number of vertices. I sum over all the subset of edges which have no source, and I have a weight which depends on how many edges I have selected. Okay? So I'm going to explain that. Now, what's happening instead of, so I will write everything again, but what's happening instead of looking at the partition function Z, I look at ZA. If I look at ZA, if you remember, I just need to multiply here by ZA, by sigma A. Okay, so now I'm looking at this guy here. It will be equal to what? So of course, what I said here, it was in the free boundary, and we deduce what it is. So what does it change? Well, it changes that now, if I multiply here by sigma A, it's not the source of, it's not just that. I mean, what I get is the source of E union, or not union, but like, it's the symmetric difference. If I multiply by sigma A, okay, so this guy is just the product of this, okay? Then I do times the product of the sigma x when x belongs to A. If x belongs both in the source and in A, it will disappear. So I just need to consider the x which either are in the source and not in A, or in A and not in the source. Okay, so this is exactly the thing here. And so what you will want, if there is a sigma A here, what you will want in the case of the free boundary condition, you will get 2 to the power v, and you ask that, well, now the source of E A is equal to the empty set. Which is exactly the same as asking that source is equal to. So to summarize, what do we get in the akntQ expansion? So is it okay for this? So to see if you have understood, like, what's happening, like, so as I told you here, it's in the case of the free boundary condition. What's happening, first of all, for the partition function if I am in a plus boundary condition? Well, if I am in a plus boundary condition and I look just at the partition function, which means that I'm just considering all this part here. And then I will get also that it's 2 to the power v. So v will be actually, here it's the inner vertices. And here I will have a condition which is not that the source is empty, but I have that the source must be inside the boundary. Okay. And if I put sigma A, what I will have is that, well, I must have that the difference, the symmetric difference between the source and A must be in the boundary. What does it mean, all this? Because it looks maybe, still complicated, like, oh, there are sources, there are things like that. But think about it, like, I have my graph and I select some edges so that I don't get any source. Yeah, I mean, this actually. What does it look like? It looks like a even better, a closed path, a loop, actually. Okay, so in fact, when you are going to consider subset of edges where there is no source, or suppose this is also maybe in red is better. What you see is actually just kind of some loops, you know, some configuration which looks like union of loops on your graph. So it tells you that in fact, Ising model in the akntQ expansion, it will be like the partition function will be something of the form some constants that I don't care. And if I'm in free boundary condition, the picture I will have is the following thing for the partition function. I will have just a sum of her kind of loops like that. I know. So I sum over all those guys, and I have a weight, which is just something of the form certain constant to the polar, the number of edges selected. Now, if I insert A, imagine now I want something with a source, let's say. So this guy is a selection of edges which has two sources, this and this. What does it look like? It looks like a bunch of loops and a path from here to here. Okay, so when you have ZA, actually, what you will have is the sum of our things which looks like this. Like you will have a bunch of loops, path, which connect the different points in A, and again, C to the power of the number of edges. This is in the case of the free boundary condition. And typically, I mean, it looks nice because in the free boundary condition, if I look at the partition function where I insert only one spin, it should be related to the correlation of one spin, should be equal to 0. Is it possible that I get like a non-closed path which goes from one point to itself? No, because it will have to close. Okay.
Well, in this case, our A is just
This guy.
all the points.
This guy, yeah. Okay. So let me write it slightly better again, so that it's even here. Okay, so this is for the free boundary. And then for the plus boundary, let me still write it not here, just that you can fit it. For the plus boundary, this will be equal to the sum of her. You will have loops plus, you can have path on the boundary. This is okay. Times a certain weight. And if I put some spins inside, what is the kind of image I have is, well, it's an image where I have also paths which connect those points, plus possibly the points are connected to the boundary. So this is really the image to kind of keep in mind, okay? If you want to write it well, so what I'm claiming is, typically if I want to compute the expectation free sigma A, this is a ratio of two things. Sum over all the set of edges with the sources is equal to A, H beta to the power E over some the sources is actually equal to empty H beta. Okay, it's just a ratio of two things. I'm asking here the source to be equal to A, here I'm asking the source to be empty. So now if I put the plus boundary condition, it's exactly, I mean, it's again what I've said. You need to have that the symmetric difference of sigma E and A is included in the boundary. And here you will ask that the source is included in the boundary. Okay. Is it okay this? So we write it again. So to finish, yeah, I'm not going to do more, but yeah, sorry. So if I put the plus, what I need is this is equal to this union, some guys, G, like some guys which are included in the boundary, and this is included in the boundary. Okay. So just to finish, why is it called the item for expansion? If I take the partition function z, if I want to write it as a perturbative expansion of the partition function, what do I have? Well, I have the case where, so z, remember it's this part here. I have the case where, well, I don't select anybody. Okay, I don't select any edge. So I have something which is proportional to 1. So this is, I don't select any edge. Okay. You agree? Then I have the case where, well, I'm going to select some edges, but of course it must do a loop. So I want to have like the minimal number of edges so that I create a loop. It's actually 4, you know, and so it's like I'm going to select 4 edges like that, and a little everywhere. Okay, so it will give me like a certain coefficient here, which is how many. It's actually how many faces I have times h beta to the power 4. Plus, and we keep on like that. Now, well, it is a good perturbative expansion if beta is, if term h beta is close to 0. If term h beta is close to 0, then, well, I'm doing a kind of expansion, like as we already think about it, which is actually equivalent to the fact that beta is close to 0, which is equivalent to the fact that the temperature, which is 1 over beta, is large. Okay, so if the temperature is large, you can see it as a perturbative expansion, in the sense that the first terms are bigger than the terms after. Okay, it doesn't mean that this expansion holds only for high temperature. This expansion, you have seen, it's just applying what we have done there. Okay, it holds all the time. But if you want to see it as a perturbative expansion, you need to have beta small enough. In particular, something which is important to kind of understand is that what does it tell me, those guys, those kind of expansion, like what is it, those edges? Well, we said when the temperature is very high, we expect to have only this guy here. So we expect actually to have no edges selected. And the more the temperature go down, the more you expect actually, you know, to have more and more edges selected. So those lines, actually, in the high temperature expansion, you should actually consider them as kind of line of order or line of influence. Okay, so typically, yeah, when beta is equal to 0, you know that when beta is equal to 0, the temperature is infinite, and you expect everything to be uniformly distributed. So there is no influence between different vertices. And in particular, if you look at the expectation of sigma x, sigma y, you expect to be equal to 0, because there won't be actually any path going from, there's no influence between x0 and between x and y. Okay, so those lines, you have you have really to understand them as a kind of influence line, or like lines which drives actually the correlation between different spins. Okay, this is important to understand because it gives you a more physical feeling of what's going on here. What's going on here is kind of uniform random spins, and then you have some lines which are going to force the spins to align kind of along those lines. Okay. We'll see next time if you do the low temperature expansion, it will be all the opposite. The lines which will appear will be lines of disorders. Okay. Can you give me just 2 minutes to tell you just the other basis or not? Just so that you can do the exercise at home, it will be kind of easier. So just the other expansions to tell you what will be the other expansion, and possibly actually there is one that we are not going to do because it will be too late at the end. Next time. We have seen here basis, which was 1 and sigma. This gives you the I temperature expansion. Then there is another basis, which is just, well, does sigma is equal to 1 or does sigma is equal to -1? And so you are going to write your exponential beta sigma as exponential beta. You have, well, is it equal to 1 or not? If it is not equal to 1, okay. So this is related to what you said last time, the -2 beta, if you remember. And this gives you the low temperature expansion. So you just apply everything here and you try to understand, okay, what is this when I replace fi by those two functions? Then there is another one, which is to look at 1, actually, and to look at, to look at the fact that sigma is equal to 1. You can also say that. You can say, okay, I look at the minimal energy, and then I just look at perturbation according to this minimal energy. Which means that you write exponential beta sigma as the following thing: exponential beta, exponential -2 beta plus 1 minus exponential -2 beta to the power -2 beta delta sigma equal 1. You see that if sigma is equal to -1, what you get is just this term, exponential minus beta. If sigma is equal to 1, well, this guy will give you actually a 1, and so you get exponential beta. So you're just decomposing here in terms of the minimal energy and variation. You are doing an expansion according to the minimal energy that you see on the edge, okay, which is exponential minus. And this will give you what is called the FK expansion. What is nice is that in the FK expansion, you are going to be able to write the correlation of spins, not in terms of a ratio of two things, but really as a probability of an event happening, which is nice because the first ones, in some sense, you can see it as the high temperature expansion is more a ratio of two probabilities. This one, it will be really like the probability of uncertainty. So maybe I will just, for this one, I will just give you the result. I won't do all the expression. And then 1 sigma squared plus the trick, so which is called the switching lemma. So you know what is the expansion here? It's just sum of beta to the power n factorial expansion over n factorial. This actually will give you the correlation square as a certain probability of a certain event. And the probability will be just this percolation, where on each edge you have an independent random variable. So in some sense, you go from those two, they are nice because they tell you really something. The lines are disorder lines. These lines are kind of influence line. This one, you begin to lose a little this physical notion, because what's more, it's a percolation, but with a non-local term, which is people maybe don't super like it, but in math it's nice because it's still kind of a percolation. And then you manage to actually remove all the non-locality, but by looking at the square of the Ising model, and then you go to a percolation where it's not only 0, 1 plus a non-local term, it's really 0, 1, and 2, and 3 on each edges. And now really all the variable on all the edges are independent. Okay. So next time what we'll do is, we'll do that because it's not very complicated. I will just give you the result on that. And we will try to do that. And using that, we will have all the inequalities and all the things we want to finish the magnetization. You can really try to do that. I mean, it's a good exercise. You can really try to do this and that if you want. To try to compute what's happening here. I can give you just one last trick is here you have to think about the dual. If you want to understand what it means, try to understand on the dual what's going on. Because you will have things like, I want sigma x different from sigma y. It's kind of complicated to understand what it is. If you look at the dual edge, then it will be way easier to understand things. Okay. Thank you very much. Sorry for.